boa tarde a todos. Essa é mais uma atividade do Observatório da Inovação e Competitividade da USP. Hoje, tendo como palestrante o professor Matthias Wellers, diretor da AVL Powertrain do United Kingdom. O tema vai ser Future Powertrain, as tecnologias que estão sendo desenvolvidas e aprimoradas e que farão parte do sistema de propulsão veicular no futuro. Tais tecnologias visam atender a demanda atual por veículos mais eficientes, econômicos e menos poluentes e alcançar os limites estabelecidos para emissões veiculares futuras. Esse debate está sendo transmitido ao vivo. As pessoas que quiserem fazer perguntas, eu vou passar o e-mail para que essas perguntas sejam feitas ao final do programa. Infelizmente, nós não temos tradução simultânea. A apresentação será feita em inglês. A maioria da audiência, eu acredito que aqui, tanto dos que estão nos acompanhando pela internet, enfim, eu acho que tem condições de fazer o acompanhamento em inglês. E depois a gravação do programa ficará disponível no site do Observatório da Inovação. Então, para as perguntas, o e-mail é IEA responde, IEA de Instituto de Estudos Avançados responde tudo junto, @usp.br. Posteriormente, no site do Observatório, quando estiver disponível a apresentação, é OIC, O de Observatório, I de Inovação, C de Competitividade, .nap, N de Navio, A de Amora, P de Pato, de Núcleo de Apoio à Pesquisa, .usp.br. Então é oic.nap.usp.br. E para as perguntas, novamente, IEA responde @usp.br. Aqui presente está a equipe do IEA: Rafael Borsanelli, da área de comunicação, Jorge Paulo Soares, que acompanha o vídeo, Sérgio Bernardo, que também acompanha o vídeo, e Sandra Codo, que fará as fotos do evento. O professor Matthias Wellers, ele é graduado pela Ruhr University, na Alemanha, e por Aachen University, também na Alemanha. Com a palavra, o professor Matthias Wellers.
Thank you very much for the possibility to speak here today. I stand up, then I can speak a little bit better than sitting. First, for sure, welcome. Thank you for the possibility. And I want to start here with some of the nationalities we currently employ in the UK. I'm representing AVL here today, and I want to start the whole presentation with a little start about AVL. So there is some commercial in it. The second part, then, I will talk about the Future Powertrain Conference, Future Powertrain Technologies, how we see in future how we can reduce CO2 emissions for vehicles. So let me start a little bit and first welcome you. Bem-vindo, I hopefully pronounce it right. You know, Portuguese is quite difficult. You don't say muchas gracias, you know. It's quite a change for me. Let me start a little bit with the company I represent. It was founded in 1948 by the father of the current owner. It was founded by Hans List, now it's Helmut List. And it was founded in 1948 after the Second World War. We Germans destroyed the world, like everybody knows. And I'm very happy that we lost, because I'm living now in the UK, it's much better. And at that time, we had to rebuild Europe. And the father, Hans List, started really with diesel engines. Diesel engine development, because it was there to produce electricity. In the meantime, it has grown from Austria right into an international company. So it's in Austria, Germany, UK, France, Sweden, Hungary, Turkey, Slovenia, Russia, USA, Brazil, yellow and green you see there, Japan, Korea, China and Indonesia and India. So there are a lot of countries we are working currently. And I must say, and I'm very happy to be in Brazil, the automotive industry is one of the really international industries. I'm born myself as a son of a judge, and he told me, don't become an engineer. engineering, you know. But engineering is a possibility really to work everywhere in the world. And this is what this company stands for, because we are a very international company. And we want to bring future powertrains into reality. When you look nowadays which concepts and which elements you have in a powertrain, there are 5 elements. You have always an internal combustion engine, or mostly. You have a transmission. You have control strategies. You have an electric drive and a battery. The future powertrains will consist of these elements. Some people say there will be only electric vehicles. I personally strongly question this, because then how many batteries do we have to produce? Imagine the amount of batteries. This company works in all these areas, and we don't only develop powertrains, which is a big business for us, but we as well develop tools to simulate and evaluate future powertrains. The complexity is so big that you cannot build prototypes of all the ideas you have in mind. So you have to have tools where you can simulate modern powertrains and test them. The other problem with these simulation things and tools is each powertrain, each company nowadays works very international. Here in Brazil we have Ford, we have Volkswagen, we have GM, we have all companies here in Brazil. Here is part done of the development, but larger parts or different parts are done in the US, in Germany, and wherever. And if you want to work really together, you have to have tools how you can translate your results into a unique language and a unique process, because the results and the work you do must fit into the process and to other people. And this is a big business for us for sure. And everybody knows the big problem nowadays is for sure as well, you have to measure everything. Everybody knows in Europe we have the new European driving cycle. Nowadays it's real world emissions. And how do you measure fuel consumption, CO2, all the emissions? There have to be proper tests, and these tests must be repeatable all over the world. So there is a big need as well. When you look at the company, for sure, it went very, very early, very international. The current owner, Helmut List, is married to an American, and this shows as well his international direction. When you look at the management level in this company, it comes from all corners of the world. And I do think he got it as well through his father, because his father was already in 1926 a professor in China. And to be honest, 1926 the world looked a little bit different in China. I do think as well in Brazil. And at that time, to be at a professorship in China for 6 years was different now to go there and give a lecture. Yeah? The current owner, Helmut List, is still one of the most active people I know, but I do think most people know him anyway. Let's go really to the thing what I want to talk about, future powertrains. I really like to be an engineer nowadays, because there is a problem in the world and everybody recognizes this. Even as well in America. We have to reduce CO2 emissions. But let's look how much CO2 emissions are really man-made. When you look at this, in reality only 4% of the emissions which are produced worldwide on CO2 are man-made. The problem with 4% man-made emissions is they can be very dangerous when they can't be dissolved. Imagine you gain every year 4% in your weight class, you get really big. And this here is as well a real problem, because when we can't dissolve these CO2 emissions, we get into global warming. And there is no argument anymore about it. If it happens or not, it is already happening. From these 4%, we have around 22%, so 1% of the CO2 emissions come from transportation. And moving just the CO2 emissions from transportation into energy, meaning if we were all driving electric vehicles with batteries, and then we produce the electric power by burning coal, that won't help us either. So we have to not only move perhaps some of the emissions to other areas, we have as well to optimize our way of producing energy and moving ourselves. And when you go further in your transportation, you have your cars 45%, rail 2%. Rail is only 2%. When I look here as well in Brazil, and I like Brazil, yeah, Sao Paulo, great, but there are a lot of trucks on the roads. Why are not more of these goods transported by rail? It would be perhaps better when you look at the overall energy consumption. One thing for sure, and this is clear to everybody, especially here, I think, more and more people move into towns. Sao Paulo is, I think, one of the largest cities in the world, but there will be more and more people moving to large cities. And the way how we communicate and how we travel will change. There is a big fear and a big feeling as well that perhaps ownership of cars can change. What do I mean with this? For example, when we all have mobile phones, but nobody owns his mobile phone anymore. So the feeling of owning something isn't that important. In my generation, when you're over 40, you still want to own a car. But the younger generation perhaps doesn't want to own a car anymore, they just want to use a car. And when this happens, as well, your expectation of this car changes. You don't care anymore about aluminium wheels or the color of the car or whatever. You care just about how expensive it is to move from A to B. And that would be a big change as well for the automotive industry. But there's more for sure. And this is our finance minister in England, Mr. Osborne. Everybody knows Europe went through a recession, through a real downturn. At that time, and this is a good thing to be an engineer, everybody recognized bankers and lawyers are not the best people in the world to produce wealth for a country. Because when you want really to be wealthy in a country, you have to produce something. You have to export something. You have to bring the wealth of your country ahead. It's not enough to cut each other's hair. So we have really to do something, and this is really recognized. And one good thing about the stock market is, one thing is for sure, the oil price will go up. So energy will become more expensive. There's no question about it. It might go down for 2-3 years, but it will generally go up. And engineering, even in the United Kingdom, where there are lots of lawyers and finance people, they recognize we need engineers. But don't be too happy in Brazil. Even in Brazil you have a quest for engineers because they're not enough. I see a lot of engineers as well coming out of China, and China is pushing ahead in engineering like no other country at the moment. There is a real movement in these countries that they recognize we need engineering. Then let's really talk a little bit about numbers and bring them a little bit into perspective. At the moment, we produce in the world 65 million cars each year. New, brand new, 65 million. And to get a little bit of feeling about 65 million cars were driven in Brazil, on all the roads in Brazil in 2010. So the world produces every year, brand new, the whole fleet of Brazil in 2010. Brand new, every year. Brand new cars, 65 million, big number. And the problem is, you could say we produce 65 million cars, but we as well dissolve 65 million, yeah? We put them to rest. No, we only put 30 million cars to rest, and that means we put every year 35 million more cars on the roads. 35 million are, just to get as well a number, every child which is born in Brazil gets 10 brand new cars to drive for their life every year. Every child in Brazil gets 10 cars. You could say as well 35 million is the number of cars currently driven in the United Kingdom. Every year we put another United Kingdom on top of the world. I know that the Queen likes it, but I'm not sure that the world likes it. So there is a real need to bring these cars and powertrains to make them better. And in all this, we produce cars. And here you see the car which was first produced 1955, the Essa from BMW in Brazil. It was the first car in Brazil. Nowadays, the cars have changed a little bit. But however the car will look like in the future, it has to fit into the society, into the local society as well. Mauro, my colleague, told me that here in Brazil there was a hype in cars when you have a little bit black plastic around and the spare wheel on the back and a little bit higher because of the speed bumps. But in reality it was just fitting into the society. It wasn't something special, yeah? The car has to fit. It has as well to fit cost-wise into the society. Sometimes you have to take costs down to sell a car. And when we build more and more complex cars and power engines and after-treatment systems and whatever, the costs go down. We have to see that we can build these powertrains cheaper. Not only better, but as well cheaper. So less complex, not more complex. Intelligence is to make complex things easy. Professors do easy things complex, but that's a different topic. The cars for sure have as well to be different. You cannot build the same thing over and over again. The people get tired of it, so they have to be different. Differentiation is very important in our society. And the last, and this is really driving us as powertrain developers forward, is the legislation. In reality, we all hate it, but it makes us tick. Because when we have to bring the emissions down, we have to have new ideas. And every time there is a new legislation, I know everybody says it's impossible to achieve this, and afterwards it's possible. The biggest demon at the moment is called real-world driving. Because it is very important to know how much fuel and how much emissions you really emit when you drive. I know in Europe and around the world often the new European driving cycle is used. NEDC. The NEDC is 42 years old. I do think 42 years ago you traveled in Sao Paulo differently today. So the question is really, does it still fit? And people think it doesn't fit anymore. So when you look at future legislations, and there are lots of things on, but I want to concentrate on the real-world driving emissions, they will come into play. And real-world driving means that we have to optimize the engine and the whole powertrain and the car in real world. And the problem there is, what is real world? But let me start a little bit with an engine, because then we take it piece by piece. When we look at an engine nowadays, we have for sure the engine speed. We have the engine speed on the x-axis. Then we have the torque and Newton meter in Newton meter on the y-axis. You see there a curve. This is the full load. So when you give full throttle, this is the torque to a specific engine speed you can achieve. When you look where the new European driving cycle is, then in reality we do not cover the whole engine map. We cover a little bit only. And not everybody drives there. Because when you start driving here and you put the first gear and you put full power, this is not in the new European driving cycle. So there are regions which are not optimized at the moment perfectly to emission standards. And as well, even smaller engines are sometimes very good in this green area, but they are not that good in full load. There are engines which are sold nowadays which need so much fuel at full load to cool the exhaust gas down. Because you don't need inject then the fuel to burn the fuel, but you inject the fuel just to evaporate the fuel and take the energy and the temperature down. And I don't think that's very good for the fuel consumption and for our emissions. So people already talk about other driving cycles. There is this random test cycle. It covers already larger areas. And the next one is you could put as well in each car into the boot a portable emission system. So you could measure really whilst you are driving all the emissions. And that would cover the whole engine map, because it would cover wherever you drive, however you drive. The problem there is, who defines how people drive? Yeah, that's a weird problem. And which town shall we take? Shall we take Sao Paulo, or shall we take Rio, or shall we take the road between Rio and Sao Paulo? Or shall we take the mountains or the seaside? Nobody knows at the moment. There's a big quest already going on. One thing is for sure, we have to optimize a whole lot nowadays. There's no question about anymore. We try really to get overall the best solution. When we take this map again and go now a little bit further, we go now from the engine the next step. So we have here as well an engine map, engine speed on the x-axis. You can say torque is on the y-axis. The blue line is again the full torque curve. These little islands are fuel consumption islands, and the little island in the middle is the best fuel consumption. The fuel consumption means in this way how much gram per kilowatt hour you need for fuel. So how effective is your engine? How much torque and energy you can get out of your fuel? You can as well use now this engine map and put it into a vehicle. Let's think about the vehicle. On the x-axis we have the speed. On the y-axis we have the traction force. The bigger black line is in reality the torque you need when you drive with constant speed. That means at 100 kilometers you need perhaps 500 Newton. At 160 kilometers per hour you need 1000 Newton. This is just the resistance, rolling resistance, resistance of the wind, your shape and whatever. Then you have as well the maximum torque curve. This is in reality the maximum torque you can get from the engine. And now we put the gears in. And the first gear is the top, the second, the third, the fourth is the lowest curve there. When you look now, when you change gear, you would accelerate full with the first gear, then you change the gear so it goes 6,000 RPM first gear, then chuck, power drop, second gear, third gear, fourth gear. I know nobody here in Sao Paulo can drive like that, because in the second gear you would hit the car in front of you. Yeah, but just to explain where the power drop comes from. This is nice for people who want to race, but now we want to think a little bit where would be the best fuel consumption. We can draw into the engine speed a little island where the best fuel consumption is of this engine. Because the engine developer goes to his chief engineer and said, didn't I do a great job? Wonderful, I have here 240 gram per kilowatt hour. I achieved that. And then they put this engine in, put it into the vehicle, and look where are now really the best fuel consumptions. And the best fuel consumptions are now in real world in these blue bubbles on the left hand side. When you look now where do we really drive, then I would say nice job done, but a little bit missed. Yeah? And what can we do? What can we do now to optimize the real world fuel consumption? Not only optimizing the engine and not only optimizing the transmission, but the whole lot. So some people might say, I have a solution. Let's have more gears. Let's increase the gears to 9. Let's see what happens then. We put the 9 gears in and we find we are much better. But it's 9 gears. You think of the costs. You remember we have as well to optimize the costs. But I tell you, some people will do that. And this is Mr. Winterkorn at the Vienna Motoren Symposium. He said he will go with 10 gears. 10 gears. I drove yesterday a Ford here in Brazil, and you had only 4 gears because you reduced cost. 10 gears, so that, yeah, I'm not sure that that's really the best solution, I personally. Let's think a little bit what else can we do. We have here the 4 gears again. What happens if we get better with our engine? Let's not be better really, I mean, in the best value, but let's make this island a little bit larger. Yeah, let's try to stick with 240 gram per kilowatt hour, but we try to make the island bigger. And there are different technologies to do that. Yeah, you can put more money into your engine. You can, for example, run the Miller cycle. This is a little bit playing with the inlet valve. Yeah, you need a variable inlet valve perhaps, but there are possibilities to really get better. When you then take this red line with 6 gears, you get already much better. So you optimize both ends a little bit, yeah, invest a little bit in both ends, and the overall result is better. The other possibility is, for sure, that we increase further this valley, yeah, this best island fuel consumption. And when we go even to lower maximum power, lower maximum torque, but we can increase this yellow island, then we get into a real good situation with 6 gears. Even when we have this wonderful island, we still have here down there an area where we have a problem, where it's green at the moment. And in that area we use then a small electric motor. Why? Why is this little green island in reality there? When a combustion engine just idles, you don't take any torque of it, you still need fuel to run the combustion engine, because you need the fuel to overcome the friction of the engine. And when the load is very low, which you take from an engine, the efficiency is low. Why? Because most of the fuel you inject into your engine is needed to overcome the friction of the engine itself. So that's the reason, for example, we have for sure start-stop in all the cars nowadays in Europe. As soon as you stop your car, the engine would idle, you switch the engine off. Because the fuel you can save, for what do you inject fuel? Just to overcome friction which you don't need? And we can do the same here. We can switch the engine off in low load points. Then we need for sure an electric motor. Because in these low end points, low torque points, we use a small electric motor to run our engine, our vehicle a little bit, yeah, with not too much force. We only need here, we have here 1,000 Newton meters, 1,000 Newton. This is a small electric motor. And then you need for sure a combustion engine, a transmission, electric motor, and a battery. Because when you want to run your car with an electric motor, you need a battery. The battery, what happens when it's empty? You have to recharge it. But when you recharge your battery, whilst you are driving in these low-end points, you can move, because you take them from your engine, not only the force to drive your vehicle, as well you use your engine to drive your generator to produce electric power which is saved in your battery. You move the working point of your engine up into the yellow area, which is much better considering the use of your fuel, the efficiency of your engine. So you artificially, with this generator, move the working point to a higher load, and you overcome this point where you are not very efficient with your combustion. And that's the way forward, and we see this happening everywhere. So it is not only the engine, it is not only the transmission, it is not only the battery, it's not only the e-motor, it's all things together. And this is a big change in the automotive industry, because up to now, honestly, you had a team which did the engine, you had a team which did the transmission, and they don't like each other, yeah, because whatever, transmission people hate combustion, and combustion people say, what is a transmission? I don't need them. So, and now you have even electric motors and batteries. And I'm a mechanical engineer. I tell you, I hate everything with electric. Yeah? But I have to speak with them now. And we have to work much more together in future to achieve such things. And the problem with us engineers is, let's be very honest, we are not the smartest cookies. Because when you look at technologies of engines, we always put something on top. When we have nowadays a real modern engine, we have turbocharging, two-stage, nowadays already. BMW has no natural aspirated engine anymore. They are all turbocharged. We have exhaust gas recirculation because we want to reduce the combustion temperature, the NOx. Nowadays we have high pressure exhaust gas recirculation and low pressure exhaust gas recirculation. Low pressure means you take the emissions out of your outlet and put it into your fresh air again. Yeah, this is really a complex system as well. We have direct injection, advanced fuel injection systems. In modern diesel engines, we have 5 injections per combustion. You have a pilot, you have a split main, you have a post, and then you have one additional, sometimes just to put fuel in, which you then burn in the aftertreatment system. We have downsizing, smaller and smaller engines. We have temperature and energy management. We look in depth nowadays, how can we bring the temperature of the engine very quickly up so that the friction goes down when you have a cold start. But sometimes the engines nowadays are so efficient that we have to have an electric heating of the aftertreatment system, because you can't get the engine the temperature anymore to regenerate. It's a real complex system. We have diesel particulate filter, catalyst, lean NOx trap, selective catalytic reduction, wow, I can read it, start stop, further hybridization, alternative combustion. And the great thing with us engineers is we put something on top but we don't take anything out. It is enormous, an engine nowadays. When you calibrate it nowadays, you need around 140,000 variables to calibrate. So you have to put 140,000 values into these ECUs so that the engine runs perfectly. I tell you, it's a mess, and it's not easy. And I want to talk about these problems a little bit more. We call it smart concepts. Whatever you do, in life or wherever, you need a process, you need tools, and you need know-how. Yeah? And whatever you do, you write an exam in 4 weeks' time. Yeah? In 4 weeks' time you write an exam. Last week you can't drink. 2 weeks before that you have to learn. And you need paper and pencil, and you need a process, you need tools, and if you want it or not, if you really want to pass the exam, you need as well some know-how. In the car industry, in the automotive industry, we are very good with processes, because we develop and produce cars for a long time. These processes handle our complexity, they look for the timing, because the timing is money. You have to reach your timing. You look for costs. In the tools, we look nowadays for guided calibrations, design of experiment, steady state. We need better tools to find and define all these values. For example, if I take alone here in the room at the moment, 20 people, I do 2 teams, same engine, and you calibrate it. There would be 2 different calibrations. And when you put both then in serious production, one calibration fails and the other team has to find the mistake. You can't. You have no idea how they did it. So you need really processes. And the know-how is changing rapidly. Up to now in the automotive industry, and when you look at the management level, look at the senior management, they're all mechanical engineers. Often they have no idea about electronics. Let's be very honest. The 2 electric motors up to now were the wiper motor and the starter motor, and they both came from Bosch. Yeah. And the battery was that big, had 12 volt, and came from Bosch. But now, when we want really to produce and develop future powertrains, there is a big need to build up all this know-how. And it is a real challenge. All these companies look for universities for new know-how. Some companies even think there might be a breakthrough in battery development in 5 years' time and we all be happy. So we have to invest a lot to get these batteries better and the e-motors better and as well durable. They have to last. And I want to show you a little bit what I mean with know-how. And here you see the air path of a diesel engine, but it could be as well the air path in reality of a gasoline engine. It's almost the same. Let's go through this. From 0 to 1, it's the air filter. The air goes in. Then it's measured in the mass airflow sensor, MAF. Then it's compressed in the compressor, and when you compress air, it's getting compressed, pressure goes up, but as well the temperature. To get the density up again, you cool it. So you go into the intercooler, then you're at 0.21. From 2.1, you put 3.3 in, that means exhaust gas recirculation, exhaust gas which was cooled. You burn it, the exhaust gas comes out at 0.3. You cool some back, 3.1 to 3.3 through the EGR cooler. The rest of the exhaust gas is used in the variable nozzle turbine, and then it goes into the after treatment. And nowadays everybody talks about model-based control. Let's try this once. And here you see the model, for example, from the intercooler. It's 3 equations, it's mathematics. It's not that difficult, because when you look from the path, the mass flow in 0.0, 1, 1, 1, and 2 is the same. Yeah, and we measure it. So this is the mass flow we measure. We know this mass flow. The change of the mass within the intercooler over time is the difference between the mass in and mass out. That's really highly physical difficult. And then you take as well the ideal gas equation, and you can build a model of this intercooler. The individual models might be easy to understand, but when you put them all together, it's getting more complex. And everybody knows when you connect all these wonderful things, it's much more difficult to understand what really happens. But you have to understand each individual component to get to model-based. And the task of the people nowadays is to calibrate then all these values which are necessary. Some of them you can take out of physical data, length, volume, whatever, but some of them you have as well to identify. And there I want to give you an example how we think the future could look like. And therefore I want to talk about one little example, the turbocharger speed, and then I give you an outlook what I think how other propulsion systems might look like. We have here the range extender, where we as a company have invested heavily in R&D, and I'm allowed to show there afterwards a film, and that will be the end then of the presentation. So let's look a little bit at the turbocharger speed. What is the problem? You have here a turbocharger. A turbocharger in the automotive industry consists of 2 parts in reality. It's a turbine. In the turbine, the exhaust gas goes in, and you try to get out of the exhaust gas as much energy as possible, and you do this usually with a variable nozzle, so a variable geometry of the turbine. There you have an actuator. The electric actuator is shown in the picture as well, and the energy, which is an rotation energy, goes into the compressor and compresses the fresh air. So you have afterwards more dense air to go into your combustion engine, and you can get more power out of the displacement of your engine. So, but the problem there is the following, and some people take then these cars and drive up and down the hills. Why? Imagine you want to achieve a specific boost pressure, a specific pressure after the compressor. Might be here. And then your ambient pressure when you go up the hill goes down. So you have to achieve more work to compress your air. This can only be achieved in a compressor when the compressor turns faster. But when the compressor turns too fast, it goes bang. So you have to find an adjustment of the boost pressure which you can achieve in the height. That's as well the reason when you take your cars, you go up the hill, even a compressor engine, with these wonderful things, your power in the top of the hill isn't as high as in the valley. It's like a human being. When you're up when you run up the stairs, is always more difficult than going down. But taking that apart, let's go back. We are all engineers. We see here the theory of a turbocharger, of a compressor. We have mass flow in, mass flow out. We have temperature T1 in, temperature T2 out, pressure 1 in, pressure 2 out, and we have the speed of the compressor. When we look then how we usually describe compressors, it comes immediately the compressor map. The compressor map is here shown on the right-hand side. You see on the x-axis the normalized mass flow, on the y-axis the maximum pressure ratio. Pressure ratio is output pressure to input pressure, normalized mass flow, and there comes thermodynamics. I'm sure you guys are much better in that than I am. I just read it in a book, because thermodynamics was never my forte. So you take the mass flow, you take the input temperature divided by the reference temperature, square root pressure reference divided by input pressure. And you have your normalized mass flow. When you know the normalized mass flow and you know how fast your turbocharger, the compressor, can run, so that you know the maximum speed, then you can draw in the maximum speed and you get out of this graph the maximum pressure ratio. And now we come to highly mathematical equations. The maximum pressure is maximum pressure divided by P1 multiplied by P1. I understand that equation at least. So, and out of that you know your maximum pressure, which is achievable from this turbocharger, from this compressor, depending on ambient temperature and ambient pressure. And all these functionalities which we do will have two parts. You have always a theoretical knowledge, you have always physics behind it or chemistry, and you have an experimental knowledge, because you have to adjust what you do to the real world. Yeah, the compressor isn't an ideal compressor. Here it has losses, it has friction and whatever. Therefore you have some experimental data. And all these functionalities are the same. And we are very good in PowerPoint engineering. And now please look. This is wonderful, isn't it? I can do it again. It took me a day, by the way. So, third time lucky. So, but out of these ones you can create then again this functionality which I was talking about. When you look at it, always start please at the output, never at the input when you want to understand it. So the maximum pressure is the maximum pressure divided by P1 multiplied by P1, highly mathematical. So pressure max divided by P1 is the maximum pressure ratio we get out of the map. Multiplied by P1, we get P1 on the left-hand side there, we just multiply it with it. We need for this map the normalized mass flow as an input. Therefore, we take the mass flow again, multiplied by the square root of T1 divided by Tref, multiplied by Pref. Over there we take a map. Why? Because the ECUs, electronic control units, are very bad in calculating square roots. But you can build a map with the data you think you need for this calculation. And then you divide it by P1. And you have the whole functionality depending on ambient temperature, ambient pressure. The only thing now is we have to find these curves. And therefore you go into an identification algorithm. That means you take a vehicle and you put measurement equipment on. You put on the compressor a speed sensor so that you know how fast does our little compressor really rotate. And the rest of the data you have there. Because what you do is you take the turbocharger speed, you calculate the pressure ratio and the normalized mass flow. And out of it, abracadabra, comes a very, very nice thing, but you have to understand these squares. And this is the compressor map. And you can calculate the compressor map by yourself. This compressor map goes then into this curve. And ready. This was one of 140,000 variables to calibrate. One. You can imagine how complex nowadays these systems are. But we have all to understand much more the physics, really where it comes from, and we have as well all to take the knowledge of other people, how then to get these data the best way. You need to describe the test procedure, You have to describe how to use these tests, if the test is good or not, so you have to evaluate the quality of the test, and then you have to put the data in and test it again. So there's a lot of work. Let's talk now something about nicer things, because this was just one example of one variable. As I said, 140,000 we have to calibrate. And I tell you, some of these variables were never touched. They are dead, you know, they're zeros or ones. But still you have to check these variables. For example, I can tell you one thing. There is one variable, for example. In a hybrid vehicle, you have regenerative braking. Regenerative braking in a hybrid vehicle works the following. You drive and you want to use the energy of your car when you brake to load your battery again. So you have a small generator in reality in your wheels, and before you use your usual brakes with the disc and the pads, you use a generator to make it more difficult that the wheels turn, so that you can take the energy out of your vehicle. But when you put them really your foot down and you really want to brake hard, your usual brakes still have to work. And there's a little delay, a time delay. Some functionalities have that. And when that's wrong, you crash into the car. Imagine you put this to 1 second and to 0.1 second. Because when you put it to 1 second, your brake works 1 second later. You can try this today when you drive home. So there are real critical data which have to be checked. And it's not easy. And you can imagine how many vehicles you have to produce nowadays and develop. There's a real task in front of us. But let's talk a little bit about something nicer. A lot of people talk at the moment about batteries. And here you see a little bit the battery costs. We can argue if these are the right numbers, and they could be lower nowadays or higher. I don't want to talk about specific numbers. But when you drive 160 kilometers, let's say the battery costs between 10 and 20,000 euros. If you want to have a battery in your car which brings you 160 kilometers. So, and when the 160 kilometers are over, then you have to recharge again. There's another way, perhaps. And this is something where we work very hard on. It's called range extender. So, what you do is you take a smaller battery, you still drive electric, and the smaller battery doesn't bring you as far. Perhaps 50 kilometers, perhaps only 30 kilometers, but the battery is smaller and therefore cheaper. And still covers most of your travel, because when we are all honest, how far do you travel each day? 50 kilometers max in reality. When you travel more to work, move 50 kilometers, let's say. 50 kilometers, and then when you want to go further, you have to recharge your battery. When you recharge your battery, you have a range extender. This range extender works in reality quite easy. As I said before, you drive with electric motor, battery. The battery is now charged with a range extender. The range extender is in reality a combustion engine, and this combustion engine is immediately connected to a generator. So it's like a small power station, yeah, which produces your electric power, which you can feed then into the battery or drive with through your electric motor. But mainly your travel is done by the battery, and you can recharge your battery as well with the grid. But when the battery is empty and you want to go further, you'd use a range extender. The good thing with this is you can reduce the batteries quite dramatically and you save money. And the range extender is by far not as expensive as shown here in these numbers. So you cover still most of your travel electric, but when you go further, you can. And we work there on a rotary engine as a range extender, and the rotary engine has not the best fuel consumption, I know, not the best thermodynamic efficiency, I know, and not the best friction, I know as well, and not the best durability, we can argue about, and it's difficult to produce, and so on. But you have to understand this is a concept. And we took the rotary engine. Why? Because when it starts, it doesn't shake. Because when you drive and it starts, you don't want to have this shaker. like starting an engine. That's not very nice when you drive and then it kicks in. That was our belief in this. There's another reason I will show you as well. But here you see, and here you see the rotary engine. We say Wankel engine. The rotary engine is immediately connected here with the generator, which is shown in red. The great thing about such a range extender is not only that it's very compact, but it's not connected to any wheel, as I said before. So in reality, it can run in one operation point only. You can optimize your combustion engine to run torque and run engine speed. Because it runs, when it runs, it just generates force which is used in the generator. And the other good thing is the generator can be used as an electric motor. When you start it, you bring the whole engine to the speed you want to, you start to fire your combustion engine, and the generator works then as a generator, not anymore as a motor, and you bring your energy out. So it's a very compact and a very nice system, because your engine doesn't go transient anymore. It's just steady state optimization. And the other reason for a rotary engine, and this was one of the reasons, it is dramatically compact. So it takes much less space than a normal combustion engine. And we tried it. And when you have a small concept, then you first put it together so that you can put it into a car, and here you see the whole realization of it. So the blue arrow you see the air in, red arrow air out. In the middle is our rotary engine together with a generator and all the systems we need to run this range extender. And then it is small, we put it into a Mini to show really how small it is. Because in this range extender we had the possibility to put in, and we still had back seats. There were some concepts with electric vehicles, they had no back seats anymore. We didn't want that. We wanted to have a full usable car. And the good thing with this range extender is the battery isn't as large. The battery still fits into the tunnel and into the tank, because you don't have to go 160 kilometers, you only go for 30, 40, 50 kilometers, and after that the range extender kicks in. So, and with this, in reality, my presentation is almost over, because I can show you now a film. The problem with the film is that in the setup here, it's very difficult to get the noise. Let's see if the noise works. Yeah? No, it doesn't. Let's see. You see, it doesn't work. Yeah, but what I can explain then a little bit what is happening there. We had the possibility to do it together with Audi, this concept. With Audi, and that was quite nice because we are allowed to show this. Perfect here, in. Perfect. And then I can... sure we engineers have to learn to be a little bit more commercial astute, because I do think we are a little bit undervalued sometimes. I'm coming out of a lawyer's family, I tell you that one. And there's one big thing about powertrains and powertrain development: it's really fun, and it's great. And since I'm in UK, it's for sure as well great in Great Britain. But I do think as well they need some help. So just to say one final word a little bit about our little enterprise in the UK. It is great to be in UK because it's the center of the international business. And when we look how many engineers we employ, we have 1/3 British, 1/3 European, and 1/3 from the whole world. And there are more and more companies as well coming to Great Britain, like Chinese companies, to put their development centers there. In powertrain development, and this is a nice thing to be an engineer, you can work all over the world. And nationalities really do not matter in our business at all anymore, because we need engineers worldwide, everywhere. Not only in powertrain, not only in UK, but everywhere. And I do think I made the right decision not to become a lawyer. I hope at least. And with this, I want to thank you for your time, and hopefully wish you a nice day in this wonderful area here with the nice weather, which I miss as well in UK. Thank you very much. Okay, yeah.
Obrigado pela apresentação de Matthias Wellers. Nós estamos fazendo a transmissão ao vivo, então todas as pessoas que forem fazer perguntas, por favor levante a mão, que obrigatoriamente precisa passar o microfone para que ela seja gravada, senão a pergunta se perde. As pessoas que tiverem alguma dificuldade em fazer a pergunta em inglês, o Mauro Giroldo, que acompanha o nosso convidado, vai auxiliar na tradução. As pessoas que quiserem fazer perguntas pela internet, que estão acompanhando pela internet, tem um número muito grande de pessoas acompanhando, favor escrever, enviar a pergunta para iearesponde@usp.br. O e-mail é iearesponde@usp.br, e toda essa apresentação, mais as perguntas, estarão disponíveis no site do Observatório da Inovação e Competitividade, oic.nap.usp.br. As perguntas estão abertas. Quem quiser se inscrever, por favor, levante a mão. O Rafael vai passar o microfone. Por favor, se apresente, só para deixar registrado, por favor.
Celso Barbosa, Instituto Senai de Inovação. Thank you for a nice presentation regarding the last news in powertrain development. And I would like to send to you a question regarding the materials. As you taught, the conditions of working conditions of engineers are pretty more extreme, from the point of view of pressure and temperature. And my question regarding what is the status of development of material to face these new challenges. For instance, for the valves itself in the engine.
I do think you're absolutely right. I'm not a material expert, but I know that this is very important, especially with the temperatures, because with the new combustion systems, we try really to bring the combustions to the optimum. But it's not only the temperatures, as well the friction. We have to reduce the frictions in these engines. The challenge is that these small engines, which are so pushed to the limit, the friction goes up as well, because you never get an advantage without a disadvantage. A highly boosted small engine nowadays has high friction. So the question sometimes is as well not to concentrate the power so much, but perhaps to derate the engines. That means perhaps not 1 liter engines, but 1.6 liter engines with better combustion system, as you said, but not the highest power per displacement. So you derate really your engine, you reduce perhaps the specific power. And the newest thing when you look at combustions, it's at the moment the Miller cycle, because you can nowadays actively change the inlet valve. Yeah, it's not, as I said, not only the material, it's then as well the actuation. And when you do that, you can get into a thermodynamic better situation of the combustion and using these Miller systems. I'm not an expert either in combustion. That's always a nice thing when you look at engines, you know. There are so many areas you have to concentrate in. And I know just that it's the biggest problem we face nowadays is still the friction of the engine. We have to reduce the unused energy losses, yeah, or the energy losses.
Mais alguém?
Eu tenho monte de perguntas. Vou fazer em português, fica mais caro, tá? Eu vou fazer em português, in order to not submit you to awful English. Very well. A questão é mais ou menos assim: quando eu uso um motor de combustão interna combinado com um câmbio de relação variável, CVT, eu consigo trabalhar no ponto máximo de otimização do meu motor. O quanto isso representa no ponto de máxima economia em relação a um motor de combustão comum com transmissão de marchas escalonadas?
The question here is really the difference between the CVT and the transmission, the manual transmission. Why we don't use CVT that can reach the best point operation, the maximum efficient operation?
You're absolutely right. There was a big movement, I do think, at that time from Volkswagen as well, to use CVTs. The challenge with all these technologies is as well you have to sell them. And they had really the problem that the customers, us as drivers, didn't accept this, that the car was running like a washing machine, you know. I mean, constant speed, doesn't go down well with us. We want to have this gear change. We want to have this. I don't know why, but we are used to it, guys. Yeah? It sounds ridiculous, but this is one of the reasons. The other reason is that it's as well again friction. Yeah, these transmissions need friction, and there's losses. And isn't a double clutch system perhaps even then better? That's a problem. And the CVTs have as well a limitation of the torque you can transfer. But you're absolutely right. For smaller cars, it might make sense. The challenge nowadays of the automotive industry is there are so many possibilities, and they can't use all the possibilities. Double clutch, wet double clutch, dry double clutch, manual transmission, CVTs. They die afterwards with the possibilities, and they have, in reality, we as engineers have to reduce complexity in a way, not only in transmissions, but as a whole concept, because otherwise it's getting as well too expensive. They are not cheap, these CVTs.
Oh, how much is more higher price of the CVT in case of the normal transmission or automatic transmission?
Got me, I have no idea. And I do think everybody who would say, I can tell you now the price, it always as well depends on how many do you sell, in which power region, in which orientation, for which car, how much space do you have. Space is getting a bigger and bigger problem. So how much space do you have for your transmission? When you have more space, you can take perhaps a little bit cheaper technologies and you save money. When you have no space in your powertrain, you have to go for higher whatever materials, like the gentleman asked. It's sorry, blank, can't tell you the price. But we are very happy to study it for you.
Nós somos um time. Deixa eu te fazer também.
Perguntas?
Ninguém vai fazer pergunta mais? No more questions?
I'm sorry, I don't want to monopolize you, sorry, but can you say something about the acting song cycle against the auto cycles? I have no idea how to the difference between these two systems.
Yeah,
thank you.
As I said before, we use here often. I talk about the Miller cycle, which is in reality, I think, the Aitken cycle when it's a turbocharged or compressor engine. What you try to do is you have a longer exhaust. How shall I say? When a working cycle, so less compression and more exhaust cycle. That means more working cycle. So you try, in reality, to change the thermodynamics in the way that you close your inlet valve earlier, so that you have less air in reality in your combustion chamber, but you use the whole working cycle, so the whole time when the how shall I put it? You know, without drawings, it's always difficult for an engineer to do it verbally. When the cylinder goes down in the working cycle, so to use the whole cycle as a working cycle, so you really expand the whole time, and that is more efficient. The problem with this is that you don't have so high power, because when you let the fresh air in and you close your inlet valve earlier, yeah, then you close your inlet valve later, so that you press something of the fresh air out again. You can do that as well, yeah. Then you have less air in reality in your working cycle, so you can as well inject less fuel and you have less power. But you use this in a longer expansion. You use the whole expansion, so you have a better working cycle. This is what we see happening. Usually, as I do think I've made a small mistake. Usually you close your inlet valve later and you press some of the fresh air out again, and then you have less fresh air when you close your inlet valve. You inject your fuel, but you use this less air with the fuel in a longer expansion, and that works quite nicely, but you don't have the whole power. You don't have so much power. When you have then a variable inlet valve, then you can change the inlet valve timing, and you can use the less power when you lose less power, and you can close your inlet valve earlier when you need more power. And that's the way the combustion people work on currently.
It works with this, like the very ancient stage.
Yes.
Almost like
Yes.
very.
Yeah. Well, let's see that it works. Huh?
Você quer fazer mais uma pergunta?
I could ask the guy all day long.
I don't know everything.
Sorry, the last question. Talking about the all-wheel drives, I always think you're tractioning all the wheels all the time. In my mind, is one way of losing energy, because we don't have it. Even in the cities, in my mind, it's ridiculous to have four-wheel drives, but the guys love it. Well, what can you say about it?
Yeah, and I can tell you, even more people who drive four-wheel drive think they can stop even faster. Yeah, I heard that as well. That people think when they have a four-wheel drive car, they can stop faster, and I tell you that's absolutely stupid. Yeah, because the brakes always work on four wheels, but it's just a demand of the market. You know, when people want to buy something, they get it. It's the same, sorry to say, with these big engines. Yeah, does it really make sense still to have V8s? But I'm one myself. I love to drive it. Yeah. Yeah. So, but it's a market. We are not. We only change our habit when we have to. When the fuel becomes more and more expensive, I tell you, people go to smaller engines. When the fuel is cheap, people love big engines. Yeah, exactly. It's the same. Yeah. But you're right. I love four-wheel drive as well sometimes.
I'm sorry. And I here in Brazil we have so few hybrid vehicles in general, and once I asked for a taxi driver that nowadays is running with Toyota Prius, and I asked the driver, and it allowed me to drive one of this car, and well, what can I do? It's my only possibility. And I tried, and the moment that it starts running the engine, the internal combustion engine, in fact, I hardly noticed that it was running. But the difference between the piston engine and the Wankel engine is that noticeable?
You have to say, I hold my hand up. We are as well companies who want to go sometimes, and this is expected from us, new ways. Yeah. When we only go the ways which we see immediately as possible, then people wouldn't need us anymore. And this was a real research project as well, and we wanted to try if this works with this rotary engine. It works very well, but it's not the best fuel consumption. You're absolutely right. But talking about things here in Brazil, what I don't recognize is any photovoltaic systems. You know, you have the sun all day and there's no photovoltaic system. In Germany we don't have sun and everybody has this photovoltaic systems on the roof. This is a question I would ask as well the Brazilian government, why don't you go with this? Sorry.
Hi, my name is Pablo. I'm a mechanical engineer, and I was just wondering, what do you think about the development of the contact in between the crankshaft and the follower in relationship with the injection of fuel? I mean, do you think it's worth it for the future to work in the contact to minimize friction in that contact in particular, or would it be better to install all of the systems in fuel injection? Is that that's what I mean?
Yeah, the fuel injection, you know, in diesel engines, Volkswagen went a long time with their unit injectors. Yeah, the problem with these unit injectors is you do not have the freedom when to inject, and that's the reason everybody went to common rail, because it's not the most perhaps the most effective system, yeah, but it gives you the full freedom when you inject your fuel. And we will see this in gasoline engines, as well, because you want to have the best fuel consumption at each working point of your engine, and this best fuel consumption and the smallest emissions, they are strongly dependent when you inject your fuel in diesel engines, and it's the same with gasoline engines. They want to inject the fuel like they want to do at that point, and you need the freedom nowadays. That's the reason we work all with these common rail systems. It has, I'm sure you could design systems which would need less energy to inject the fuel, yeah, like you said, with friction or whatever, but the freedom is there, the main reason for common rail. Imagine 5 injections, and you don't do always 5 injections. When I started as a calibration engineer, we had 1 pilot injection, 1 main, and then we stopped with the pilot over 3000 RPM, and we only had a main injection. And nowadays you do sometimes 5 injections when you are in after treatment mode, because in after treatment mode you have to inject in a diesel engine very, very late to bring the temperature of the exhaust gas up, yeah, so that you can burn your diesel particulate filter free. So you need there the freedom to inject then when the after treatment has to be cleaned. So you need even then the freedom as well. How do you run your after treatment system? So you need the freedom. That's the reason.
Mais alguma questão? Bom, agradeço a presença de todos. Antes de encerrar a participação, gostaria de convidar todos para o próximo debate do Observatório de Inovação, desculpa, tem que pôr o óculos, que vai ser sobre manufatura aditiva, aplicações e potenciais impactos nas cadeias de valor. Vai ser dia 16 de maio, às 11 horas, aqui no auditório, com transmissão ao vivo pelo site do IEA, www.iea.usp.br/ao vivo, que é o mesmo link que está transmitindo essa apresentação. Gostaria de agradecer a equipe do Observatório de Inovação. Sou Celso Fonseca, sou coordenador executivo do Observatório, Tatiana Botan e o professor doutor Leonardo Gomes, que estão aqui presentes. A equipe do IEA já foi agradecida. Agradecer muito a presença de Matias Wellers e dos seus colegas que estão aqui acompanhando, o Mauro Giroldo e o Maurílio Cassiani. Agradeço a participação de todos e até o próximo debate. Obrigado.